The birthday paradox is a fascinating concept in probability theory that reveals surprising implications about the likelihood of shared birthdays among a group of people. At first glance, one might assume that in a group of 23 individuals, the odds of two people sharing a birthday would be low, given there are 365 days in a year. However, the paradox demonstrates that the probability of a shared birthday is actually over 50%, which defies many people's intuitive expectations. This counterintuitive result highlights how our intuitions about probability can often be misleading, especially in small groups. The birthday paradox serves as a gateway to deeper mathematical exploration, inviting us to delve into the calculations that underpin this phenomenon. Additionally, it has real-world applications in fields such as cryptography, computer science, and risk assessment, where understanding probabilities can lead to more effective strategies and solutions. By examining the mathematical proof and its implications, we can gain a clearer understanding of this intriguing paradox and its relevance in various domains. The birthday paradox can be illustrated effectively using the example of 23 babies born in a hospital. Each baby has an equal chance of being born on any day of the year, which means there are 365 possible birthdays. Initially, one might assume that the odds of at least two babies sharing a birthday would be quite low, given the large number of days available. However, to understand the paradox, we need to consider the opposite scenario, calculating the probability that no two babies share a birthday. For the first baby, there are no restrictions, so they can be born on any of the 365 days. The second baby then has 364 days to choose from to avoid sharing a birthday with the first. Continuing this logic, the third baby has 363 options, and so on. By multiplying these probabilities together, we find that the likelihood of all 23 babies having unique birthdays is surprisingly low, leading to the conclusion that the probability of at least one shared birthday is much higher than one might intuitively expect. To determine the probability of shared birthdays among a group of 23 individuals, we can break down the calculation process step by step. First, we calculate the probability that no two people share a birthday. For the first person, there are 365 possible days. The second person then has 364 choices to avoid a shared birthday. The third has 363, and this pattern continues. The total number of ways to assign unique birthdays to 23 people is represented as 365 times 364 times 363, and so on, until 365 minus 22. To simplify this calculation, we can use factorials. The formula for the probability of no shared birthdays can be expressed as p no shared birthdays equals 365 factorial divided by 365 minus 23 factorial, all over 365 to the power of 23. This equation shows the significance of factorials in simplifying the calculations. After performing the calculations, we find that the probability of at least two people sharing a birthday in a group of 23 is approximately 50.7%. This surprising result emphasizes how our intuitions about probability can often be misleading, especially in seemingly small groups. The calculations surrounding the birthday paradox yield surprisingly high probabilities of shared birthdays, even among relatively few individuals. For instance, with just 23 people, the likelihood of at least two sharing a birthday exceeds 50%, which starkly contrasts with the common expectation that such coincidences would be rare. This discrepancy highlights the paradox. Our intuitions about probability often underestimate the chances of overlap in small groups. As we extend the series to larger groups, the probability of shared birthdays increases dramatically. For example, with 30 individuals, the probability rises to about 70%, and with 50, it soars to over 97%. These outcomes challenge our understanding of randomness and coincidence, illustrating how quickly the odds shift as group size increases. The implications of this paradox extend beyond mere curiosity. They have practical applications in fields like cryptography and statistics, where understanding the likelihood of shared events can inform decision-making and risk assessment. Ultimately, the birthday paradox serves as a powerful reminder of the complexities inherent in probability theory. The birthday paradox has significant implications for online security, particularly in the realm of password protection. At the core of password security are hash values, which are generated by cryptographic algorithms to transform passwords into fixed-length strings of characters. These hash values are essential for securely storing passwords as they allow systems to verify user credentials without exposing the actual passwords. However, certain encryption algorithms can be vulnerable to birthday attacks, where an attacker exploits the birthday paradox to find two different inputs that produce the same hash value, known as a collision. This vulnerability arises because the probability of collisions increases as more hash values are generated, similar to how shared birthdays become more likely in larger groups. Understanding the probability behind these scenarios is crucial for improving internet security. By recognizing the risks associated with specific algorithms, developers can implement stronger hashing techniques and security measures, ultimately enhancing the protection of sensitive information and reducing the likelihood of successful cyber attacks.